And now let's look at some higher order derivatives. So that's our discussion title here, higher order derivatives. But really, before and just like how in my style of teaching, I'm not going to rush into telling you, hey, what is a higher order derivative here? I'm going to erase the title. Let's do a couple of examples, and you will naturally understand what a higher order derivative is without me telling you what that is. Okay, so now let's start out with something that everybody at this point is so fluent with. So how about I'm given a function f of x to be x to the fourth minus 5x cubed plus 3x squared plus 2. Okay, so we have a function like that. It's a simple polynomial. It's fourth degree and all that and so on and so on. Okay, so let me ask anyone who follows along with my video to do a very simple task here. Okay, so go ahead and find for me the first thing I'm asking you to find, f prime of x. At this point, that's easy. Nothing challenging about that. So f prime here, we have learned throughout all that times prior to this point right here, when you arrive at my video lesson here. The derivative, first term becomes 4x cubed. Next term, and with the minus signs, it becomes 15, so minus 15x squared, just a simple polynomial like that, okay? Plus, so now 3x squared would become 6x, and the last term here being a constant, it's just going to become a 0. So there we go, that's our derivative. That is our derivative that we found right from that function in the beginning. Okay, nothing unusual. All right, so now, guys, let me ask you the next question here, and try to have as much thought in your mind as you can. Okay, so you see how I use a 1 prime symbol right here? It means that we take the derivative just as usual, just as how you have learned that throughout all those days right there, okay? So think outside of the box. What do you think this is? From here, I'm asking you, find f prime. Think simple and rely on your most natural sense. I don't need to tell you anything yet. Okay? Take a moment, pause the video, and think about what that prime is intended for. Alright, so I hope you paused the video a little bit and now you resumed and have some thought. Here's the idea, the prime. This is my answer, and hopefully it agrees with your thought. 12x squared minus 30x plus 6. All right, did I agree with your thought? I hope it's going to be for a good majority of viewers who follow with this, right? Your answer, the answer I have here. So what just happened here? What just happened here? So it looks like the prime, and yes, if you think like this, and now I'm about to tell it, and if you agree with me, then you're on the correct track right here. But the next prime, so the prime here, the very first one we did right here was f with 1 prime. So that was the derivative coming out of this function. And now remember a little while ago when we first getting acquainted, when we first getting to know about derivative, and in the end general derivative is another function. So this f prime is intended to take the derivative of our previously found derivative. So there it is, that's what it is. With a starting function, we found a derivative, and then with a derivative, with our found derivative, previously found derivative, now being regarded as a function again. And with this function now, I am going to take another derivative, another level of derivative. I'm starting to use that term, level of derivative. Okay, and so now, so that makes sense that the first term here, 4x cubed, taking the derivative, now gives me 12x squared. The next term is a minus 15x squared in that f prime. Now when you take the f prime, then it's going to be, the power rule comes down, the power rule kicks in and multiply that power with 15, so minus 30x and plus 6. So 6x becomes a 6. All right, so now you see this f prime prime is the derivative of f prime. You got me there on that so far? I hope you got me there on that. So f prime prime is the derivative of f prime, and f prime is the derivative of the original f. All right, so now you found it. F prime prime is the derivative of f prime, and f prime is the derivative of the beginning function. So now it's just awkward that we go for the rest of our career in calculus talk using the term f prime prime. So in that way, we just need to come up with a way to organize these levels of derivative. So think about starting with the very beginning function. The first time you took the derivative, and then the f prime prime here is the second time you took the derivative, but of course on top of the derivative right before that, the derivative step right before that. And so now this is what I'm calling it. You see, from a starting function, all relative to a beginning function. Then when we took the derivative one time, or for the first time, yes, now we call that, this is the first derivative. And yes, first derivative. Okay. Because we right from that relative to that beginning function, we only took the derivative once. So that first time giving us the derivative, we call it it's the first derivative. And now the f prime prime right here, I'm so ready to give you that term right there, but the f prime prime is the derivative on top of the first derivative. And so now, but at least in the work of taking derivative, you are at the second time taking that. So now you're going to refer to this in respect to the beginning function. Now you're going to refer to this as the second derivative. All right, but think about the relationship, the direct relationship between the two derivatives here, the first derivative and the second derivative. Then the second derivative is always the first derivative of the first derivative. Pause a moment. Pause the video for a moment and think about what I said. The second derivative is the first derivative of the first derivative. It's only second in respect to the very beginning function. Think of that. Okay? All right. And so now, as everybody have hopefully cleared out with the idea, I want you, the viewers, to start thinking outside of the box right here. Being a quality, one of the quality of being in a calculus class is that you're going to have to start pushing your imagination outside of the box and start thinking creatively right here. If now we can do an f prime prime, or formally we call that a second derivative, then now can we, I challenge you, find your own answer. Can we find an f prime prime prime? The idea is simple enough, right? Can we find an f prime prime prime? Sure, why not? If we just continue that same fashion we have been going through. So from where our second derivative here already found, and now we can regard to that as another function. Then f prime prime prime, well, the symbol is making it pretty clear, the prime of the previous f prime prime. And so that means now we're looking at taking the derivative of this right here, which gives me 24x, okay, minus 30, okay, and the constant 6 in the previous steps, now it's gone. So we turn that down to 24x minus 30, and that's our f prime prime prime. So once again, it's really awkward to call it with a name like that. So f prime prime prime. Well, obviously it has 3 primes there, but now we are going to call that, we are going to refer to that as the, see, relative to the beginning function here, because everything goes step by step. First we had a beginning function. Then we took the first derivative. Then we went on and took the second derivative, which is the first derivative of the first derivative. And now we took this f prime prime prime, which is the first derivative on top of our second derivative. Okay? And so, yes, now you have your legal right to call that. This is our third derivative. Okay, so that's our third derivative. And so now if we can have a third derivative, then start pushing your imagination even further, much further out than whatever written on my board here. Can we take the fourth derivative, the f prime 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 prime, or even the ninth derivative, the 10th derivative? Sure, why not? Okay, so now I am going to move to the other board. And it's getting to that point where I'm starting to get pretty excited to show anyone about this fun, so cool stuff right there. So yes, the fourth derivative, that's what I'm intending to head out for. Do you notice how weird the symbol is starting to look at? It's starting to look, well, ideally we're looking for the fourth derivative, but now look at how many prime symbols we have to start making. F prime 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 prime. So what if when it gets to like the ninth derivative, or are we going to say f prime 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 prime? No, it's not a good idea. So it's just a convention. It's a good convention that mathematicians worldwide agree that anytime it starts getting, it's about starting on the third derivative. When we were about 3 primes like that, then we're going to start using a symbol like this. Okay. So this thing, well, yes, I'm intending for the fourth derivative, but instead of writing f prime 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 prime, it's awkward writing it like that. So the legitimate symbol now is a superscript 4 in parentheses. A superscript 4 in parentheses. That's indicating the fourth derivative relative to our function. So our beginning function was that we took the first derivative, which is a prime. That's fine. We leave it like that as a nice, good symbol. F double prime or F prime prime, like I said, double prime. That's also one of the common terms that's being used among the mathematicians out there. So second derivative is the formal term, but sometimes for short we call that F double prime. Okay. So the third derivative, we can still stick with that. Some people already start using F with superscript 3 in parentheses. That's fine too. Okay, it's nothing right or wrong about that. You can still leave that. And so if you're leaving that as 3 primes here, you're calling that F triple prime. Okay, that looks pretty good. Formally speaking, that's the third derivative. But now when it comes to higher level of that, we don't want to continuously keep writing out the primes like that. And eventually we don't have enough board space to write 100 primes, right? Something like that. It will happen in some of your more advanced course. And so now, usually about starting at power 4, even though somebody can start doing that with the level 3 already. But fourth derivative, we start introducing that symbol, a superscript in parentheses, okay, of x. But now, yes, as that name calls it, the fourth derivative. So look back at your third derivative, one more time. Then we have 24x being minus 30 being our third derivative. So the fourth derivative now is simply just the first derivative but of the third derivative. So that means we're taking the derivative there. First term becomes a 24, no more x, okay, and the constant term minus 30 becomes gone. So here's our fourth derivative. So let me label that. This is the fourth derivative. That's our fourth derivative. And so yes, we can also find, so think about it, if I'm asking for f or the fifth derivative of f, okay, or f prime 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 prime, okay, then, but see, even using that in verbal words, it takes a lot of time to say all the primes up there. So fifth derivative, superscript in parentheses right there. So fifth derivative is being now from that step right here, then it's going to become a 0. Okay? So fifth derivative is 0. Our function started out being a polynomial, and look at the number of derivatives that we have done here. Fifth derivatives. All right, and so yes, you can find sixth derivative 7th derivative, 8, 9, 10, and so on. But starting at this 5th derivative, for this particular function, x to the 4th minus 5x cubed plus 3x squared plus 2 right there with this particular function, then starting at the 5th derivative, then and to all the later ones right there, the higher level ones, then they're all going to be just 0 and 0 and 0. Okay? And so take a good note of that. It's just a feature of polynomial. And so now, what exactly is a higher order derivative? That's what they are. Your function without derivative is here, the beginning derivative. And then we learned throughout all those days prior to this point, learn all the different techniques to find our derivative. And now we call that the first derivative. So everything we have learned prior to this point has been regarded as first derivative. And so now a higher order derivative is just any of those derivatives, second order, second level. I use the term level, but formally speaking, and all of the textbooks out there, all famous textbook writers out there refer to these as second order, formally, second order, first order, third order, okay, fourth order on the other board, fourth order, and fifth order, and so on and so on. So any of these derivatives from being the second order derivative to the higher one, we generally regard to them as the higher order derivatives. So any of these, okay, any of these is regarded as the higher order derivative. Simply higher just simply means they are higher than order 1. They are higher than the first derivative. Okay, and so that's what they are. All right, so I am going to take a moment to erase the board, and let's head into some example and looking at how easy these kind of problems are and how easy to understand they are. Then the kind of examples are going to be simple as well. However, it's worth to bring up a few so that you will learn a couple of things that will carry with you, that you will carry for your much later courses. Okay, so allow me to do that. Even you're quite early in your mathematical learning, but trust me, once you see these things, it will be maybe the first time introduced to your understanding, and then one day as you carry it on, one day it will become very beneficial for you. And so any of these examples I'm about to bring up, really unlike anything I've done before, any of these examples don't have a dead end. It's just something I bring up so that we can kind of explore. Okay, each problem as an example, and then it doesn't really have an end. Okay, we can end anytime we want, but my goal is to introduce some fascinating nature of these functions once we start learning about a higher order derivative. Okay, so the first one, example number 1. Okay, so in example 1, really, I just introduced that we looked at the function e to the x. We've seen this function. We've already learned how to find the derivative of this function. Okay, and I'm not going to even write down the instruction of what to do with this example because, like, as I said, we don't really have an end to this problem. We're just going to bring it up as one function that I want to bring that into your consideration. And then as we go on, you will understand what I mean. Okay, so right now, what's the derivative, the first derivative? Y prime. Okay, and now it's along with the example, let's also start introducing some symbol right here. So if we use f prime as first derivative, y prime is also the first derivative, and also y double prime later on is going to be the second derivative, and y triple prime is the third derivative. And yes, we can also use a similar symbol, a superscript in parentheses indicating the fourth derivative, and so on and so on. So let's explore. First derivative is e to the x, and as I already put down a list of these symbols right here, that's where we're heading into, and you already have some ideas in mind right here. So our beginning function was y equals e to the x, and then y prime is exactly the same, y prime, because we've learned that e to the x, when you take the derivative, it's e to the x. So the same here. So what about y prime prime or y double prime? It's e to the x. It's just the nature of e to the x. So you already took the second derivative. It's e to the x. What about y triple prime? It's e to the x. Okay, it's e to the x. What about the y to the fourth derivative of y right here? E to the x again. Okay, whew, that's just about enough. Okay, so you can see how special e to the x is. No matter how many times you take the derivative, or no matter how high order your derivative is, it remains permanently e to the x. That's one thing very special about your e to the x function. And it really reduces all that headache. Okay, so let's get ready for example 2 right here. Now in example 2, I want my viewers, I want my students who study with me to experience this. Let's pick, so among the trig functions, okay, among the whole family of trig functions, then we have sine and cosine. I always tell my trig students that sine and cosine really is the fundamental of all the building blocks of the entire trig function, because tangent is defined based on sine and cosine, and even cotangent and secant and cosecant. And so we're only going to have to worry about sine or cosine here. So I'm going to start out with y equals sine of x, and things will work the same with cosine, and I can leave cosine for you to explore on your own if you really want to learn and push it out of the box right here. Okay, so y equals sine of x, and so y prime, but in every example I have an intention to also show you the symbols right here. So dy dx, as usual, is this is the first derivative, okay, but instead of using the prime notation, now I'm going to use the dy dx, and let's see how things happen. So dy dx here is cosine of x, as you already have learned. Okay, so now second derivative of this. Now if we're using the Leibniz symbols like this, then second derivative is a little shocked to understand at first, but it's d square y over dx square. Okay, that's second derivative, but see, d square y over dx square is indicating that we're taking the derivative. See, d square means we take the derivative of y and we differentiate again. The idea of that symbol is d, we take the derivative of some function, and then we take the derivative again. We take the derivative again, and that's why I think about that. And it's kind of similar to d times d, but it's not really d times d, but it's kind of similar that we take the derivative twice. That's why we arrived at that d square. And then, but both times we're doing it, it's all in terms of the same variable. That's why it's dx square. Okay, so it's just an explanation of the way how we use different kinds of symbols and notations out there as well. So, but in the end, my main aim here is the second derivative of this function. But second derivative, recall for yourself again, it is the first derivative of our first derivative. That means we're just simply going to take the derivative of cosine of x. So derivative of cosine of x is negative sine of x. So aside from that negative sign here, then the second derivative almost came back to the original function. So we kind of went away a little bit to become cosine, and then we hit back to sine, but being opposite. Okay, and so the story doesn't end here. And like I said, we don't really have an end here. I just want to push it out as much as I can so that you can see and experience it for yourself right here. And there are tons of things that you can, in your later courses, will make use of this. So third derivative. So in the way how I was writing this, second derivative. So third derivative is a d cubed y over dx all cubed. Okay, but that really just means we take the derivative of our previously found second derivative. So now that becomes a minus cosine of x. Okay, and so how about the fourth derivative? So the fourth derivative here, d4y, okay, d4y or d to the fourth y, even though it doesn't mean multiplication or anything like that, over dx to the fourth. Okay, that's the fourth derivative in the Leibniz notation. This is now going to be the derivative of our most previously found third derivative. So cosine of x, but with a negative sign. So derivative of cosine is a negative sign, but now with another negative, our overall fourth derivative now is back to a sine of x. So now what's special about the trig function? You see, I normally explain in my face-to-face students that trig function itself, the graph is periodic, up and down, up and down. So even when you take the derivatives in your level of taking calculus, now when you take the derivative, it's also alternate. It's kind of going around in a loop, periodically, and eventually at some point it's going to hit back at the same function. And so the fifth derivative is going to be cosine. Sixth derivative is the same as d squared. The second derivative is minus sine, and then seventh derivative is the same as the third derivative, and the eighth derivative is again back to this, or the same as the original function. So it looks like that. It has that periodic looping nature right here. And again, in some far future course, if you are having a good passion for math after this course here and decide to go on and continue pursue into your mathematical career more formally, then there will be a couple courses that study investigate quite closely with this nature right here. Okay, and so just like that, and so now let me get back on the third example here. And the third example should be like the one I have, very similar to the one I have introduced, the idea about higher order derivative. We're going to get back to a polynomial. So how about example 3 here? Okay, our function. How about let f of x here be 4x to the fifth minus x to the fourth plus 2x cubed plus 5. Okay, it's just a standard polynomial, fifth degree, some coefficients and some terms and whichever that is. Okay, so now let's look at the derivative. Notice our function here, our beginning function started out with power 4. It's just this function started out with power 4. And it will behave similar to that introduction problem I brought up earlier. Okay, so now I am without really a goal here. The goal is to explore. The goal is to explore. So there isn't really any ending points for this. F prime. Okay, first derivative. So now you are fluent enough. That first term gives me 20x to the fourth, okay, minus 4x cubed plus 6x squared. That term becomes a 0. So we only have 3 terms in our first derivative. And yes, second derivative, f prime prime or f double prime, okay, is going to give me. So that's, well, and recall for yourself again, f double prime is the first derivative of the first derivative of the very previous level, of the most previous level. So here it's going to be 80x to the third power minus 12x squared plus, and now we have another 12x here. Okay, see how I keep taking the sequential derivatives here. And so we didn't go anywhere yet other than just keep finding further derivatives and further derivatives. So here let's look at f triple prime. And notice again that this is about the point where some author of textbook already start using f with a superscript 3 over here, even though I personally feel like it should start with the fourth derivative. But some textbook author, and it's never wrong, even that one right here can be written as f superscript 2 right here, the second derivative. Okay, so now this is going to give me, first term becomes 240x squared, middle term becomes minus 24x, last term here becomes 12 as a constant term. Okay, and so you can see that it works, it behaves so similar to that very introduction problem I brought up earlier. Well, it started out with a high power, and as we keep chopping down, as we keep going down, or as we keep getting to the higher order derivative, then the power itself on each level of derivative reducing. So it came to degree 4 here for the first derivative, then degree 3, then degree 2 as we go on. So that's the nature of polynomial. As you take further derivative, the degrees keep reducing and keep reducing. And so let's say, what about the fourth power? I mean the fourth derivative, okay, not fourth power. I shouldn't say, use the incorrect term like that, but taking this derivative gives me 480x minus 24 for that middle term. And the polynomial does get shorter as well. The constant term here is gone, vanished. Okay, so you're now ending up with 480x. Okay, and we can push that into the fifth derivative this time. So the fifth derivative of x, okay, is going to be 480. Okay, now it's squeezed into a constant term. Okay, so it started out with fifth power and fourth power being reduced down to fourth power. That's what I meant for first derivative, and it further reduced down to third derivative. I mean third power, third degree for the second derivative, and then it reduced down to second degree right here, or a quadratic in the third derivative. So in every step right here, we reduce the degree by 1, and to a point that there will be a point for any polynomial. There will be a point where it reduces down to simply a constant, and consequently, so the sixth derivative will become just simply a 0. Okay, and then starting with the sixth derivative, and I don't think I need to go any further because any of the later ones are going to be all 0 out. So that's also some fascinating nature about polynomials, that there have always been a good majority of mathematicians, a good number of mathematicians out there who spent their lifetime studying the behaviors of polynomials. Okay, so here I'm just introducing these kind of problems here just as the very, very first door, and if any of you decide to keep this and carry it on with you for your later course, you will see these natures again, and there you will start developing these ideas further out. Okay, but that is the end of our discussion for about all the higher derivatives, what they are being the higher derivatives, higher order derivatives. Now, allow me not to introduce the applications. Why are they useful? You will see the usefulness of these things as we start getting into the applications of taking derivatives and all that. And so here, allow me to only end right after the discussion here, the lecture here, right after I simply introduce for you what they are, what the higher derivatives are, and how to find them. You've been learning how to find them. Okay? And then and also as well as introducing the couple notations. Okay? And that's about it for this lesson right here. And then I will, once you are fluent with these in terms of finding out what they are and how to find them, at some other lectures, some later lectures, I promise you will see how I bring in these the higher order derivatives right there into some good usefulness. It will happen just within our quarter here of learning calculus.